Hi, my name is Grigori Filimonov, and today I'm going to explain our project, the seconds counter. Here we will see the top entity of our circuit, with the inputs count enable, clear direct, and clock, and the outputs TC60, and the outputs of both 770 space. In our case, we have here the counter BCD modulo 60, the clock generator, and the both 770 space, where all these components will be explained in detail later. Here we can see that the count enable goes directly to the counter BCD modulo 60, as well as the clear direct, where it also goes to the clock generator. And from this component, what it does, it generates a pulse that indicates whether we have from the units from 0 to 9 and the tens from 0 to 60. The clock generator is given to us because we need to modify our clock period from 15 million hertz to only 12.5 kilohertz. That will be sent directly to the counter BCD modulo 60. And the sound segments will be used to display the tens and the units.
Hello, my name is Carol and I'm going to explain you the counter BCD mod 60 that is a component of the seconds counter. First we have the counter BCD units and the counter mod 16 tens. In the counter BCD units we have the count enable, the clear direct and the clock, and the generated outputs that are the unit. And we also have the count mod 16 tens that has the load, the count enable, the UD and the clock. The load is for resettings and all the outputs reset to 0, and the count enable, when the D9 is 1, it starts counting, and the load is corresponding to D59 that we obtain with this logic.
As characterized by the counter BCD modulo 60, you may have seen that the one component is the counter BCD units. That works really similar to the counter modulo 16 tens. Well, I'm explain it. It has the count enable, the clear direct, and the clocks. And as output we have Q and TC10. In our case, inside the counter BCD units, we have a counter modulo 16 that is truncated, that later on I'm going to explain you with the state diagram. That it has the load that depends from the logic of D9, that D9 is a gate, it's an AND gate that depends on count enable and the output gate. The count enable, UTL is always 1, the clear direct and the clock. Whenever the load is 1, we're gonna input all zeros to reset it again. And then we have TC10, that is when the 9 is detected, so that it can allow the counter modulo 16 tens to start counting. As I explained before, inside the counter BCD units, we have the counter modulo 16, but in our case, we are not using all the 16 states, but we are truncating it, so we only use from S0 to S9. So S10 and S2, S15 are not used. In our case, S0 has up to 4 different arrows, starting from clear direct when it's 1, while D, it goes to the state 0. Or whenever it's already in state 0, it goes inside the loop when the count enable is 0 and the load is also 0. When it's in state 0, it has the outputs and the units for the 0, and TC16 is also 0 in our case. Then it jumps to state 1. And then it jumps to state 1 only when the count enable is 1 and the load is 0. When we are in state 1, the outputs will be 1 and TC is still 0. This happens with all the states except when we go to state 9, where in our case it has the outputs D9 and the TC16, when in our case this one is activated to 1 to enable the tens counter. And this would be the unit state diagram.
Now I'm going to explain you the 10 state diagram that contains 6 states, because from the state 6 to the 15 we don't use them. And to pass from one state to the other, the count enable has to be 1 and the load has to be 0, except when you pass from the state 5 to the state 0, that the count enable is 1 and the load is 1, so it resets the output. And then to be in the same state, the count enable has to be 0 and the load has to be 0 too. And then the outputs, the TC16 is always 0, except in the state 5, that is 1, and in the Q is the output of each state. So now I'm going to explain you the clock generator that has as inputs the count enable, the clear direct, and the clock. This clock is 15 MHz, and with this formula we get the 2000, that is TC2000, and the output we get here is 25 kHz, and when it gets to the T flip-flop, we get the clock desired, that is 12 and 5 kHz. And now I'm going to explain the counter BCD mod 16. We're going to see the RTL viewer, and here we have the counter BCD units, the counter mod 1610s with the clear direct, the count enable, and the clock. We can see the D59 that is connected to the count enable, and here the outputs. If we go inside the counter BCD units, we can see the counter mod 60 with also the clear direct, the count enable, and the clock. And here we can see the D9 connected to the count enable and the output queue and the C10.
Now, if we go inside Tools, NetEase Viewers, and Technology View, we can see a technology view of the counter BCD modulo 60. And if we go inside each chip, we see that it's a combinational circuit. And if we go inside the modulo 16, we can see that there are 4 different data registers. If we go inside to locate node, to locate in chip planner, and click inside, we can definitely see that it's a D flip-flop. I'll put it all here in model sim. As we can see up here, it's the clock periods going up and down. Here we have the clean direct where we don't care whatever happens before it. Then it sets all to 0. And when count enable, if we zoom in, it starts counting. The 10, it goes from 0, and then the units 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it jumps again back to 0. Whenever the count enable is disabled, it stays in the same state. For example, here it stays in state 1 and state 8, so 18. If we need to go identify where we have the flag of the TC60, we can perfectly see that it goes and when the 5 and 9 are detected.
And now we have to analyze the timing analyzer here in the clock to output times, and we can see that this is the maximum TCO, and in order to get the maximum frequency, we have to use the formula 1 divided by 2 TCOs. Here in the gate level simulation, we can see that it looks the same as in the functional one because we've used the same test bench, but we're going to measure the delay between the rising edge of the clock and the outputs. These delays with the cursors from the rising edge of the clock and the output D units, that is this one, and from the units to the output TC60, that is this one. The output from rising edge to T60 is the longest one. So after the counter BCD mod 60, I'm going to explain the clock generator. Here we can see the frequency divider at 2000 and the T flip-flop. The output is, as we desire, 12.5 kilohertz. Now that we are done with the clock generator, we can also see that there are 2 7/7 decoders that will represent the tens and the units. If we go inside the first one, we can see perfectly the architecture using ORs, and inside the ROM 16x8, we can see different muxes and different ANDs. Now that we are done with the Quartus Prime, we will start a new project in Model Sim using exactly the same test bench, but now we will use the oscillator of 50 million Hertz and the second signal of 12 kilohertz. If we really zoom in here, we can see how the 50 million hertz actually work. If we continue as we were previously, here we have the second clock. If we want to see the clear direct, it's exactly right here, but it's a really short signal. It's right here. Count enable, it's okay. Then we can see here that the signal generated, it's a 0. And then here it's a 1 exactly. Then we proceed here, we can see it's still a 0. And now we have a 2. We continue counting. We will see how the signal changes and creates different values in the 7th segment. Here we can also see when the TC60 it's high. In our case, it should be a 5 and a 9. Now we have to analyze the timing analyzer, and here in the clock to outputs times, we can see that the maximum TCO is this one, and in order to obtain the maximum frequency, we have to do the formula 1 divided by 2 TCO. In the gate level simulation of the counter sequence, we can see, as I said, that it looks like the functional simulation because we use the same test bench, and if we zoom a lot, we'll be able to see the delay between the rising edge of the clock, the output TC60, that is this one here. And now we are going to present the prototyping. We can also see that some things have changed. For example, now TC60 it's a node because of the architecture of our device, and also the clear direct of both chips is also negated. If we want to go inside each chip, it's exactly the same as previously. So then we need to go to pin planner and decide which pins going to which outputs and inputs. For example, here in clock, it's going to be pin P11. Then we now go to programmer and we have generated a soft file. This soft file, we need to import it to the device that is already connected to our computer. And now we're gonna see how it works in the real world. Now that we have sent the code to the device, we simply need to activate the count enable. And as we can see, it starts counting each second. If we press here the counter direct, it starts again. And if we disable count enable, it will stay forever in this state. Now we will speed up the video so that we can see all the states.